Okay, so in the previous video, I spent time just talking about literally how to plot points in one system and how to name them in that system, how there was a variety of ways that we could go about doing that. In this video, what I want to do is carry on and talk about how we can actually transition back and forth, just like we did with degrees and radians. We spent significant time talking about how you would take something in one system and turning it into the other. Their equivalent concepts are just represented in slightly different ways. So in this video, I want to talk about how do you take a point that is given to you in polar and make it find its representation in rectangular, and how can you take something that is in rectangular and express that in polar. One of those directions, there's one and only one answer that is valid, and in the other one, of course, if you're turning something into polar, there's many representations. So again, we'll talk about that as well. So here we go. Let's see how this goes. Let's turn on that image mate and go here. Now, up here at the top of my paper, I went ahead and I showed you a couple of different triangles, because what I wanted to remind you is that if you have specifically one of these triangles, now this is leading us over here into our unit circle, you're going to notice that many of the values that we have actually come from that story. So no matter what this value is right here, let's call this R, then this value right here, which is the Y value, would be that R value divided by 2. That's just what we learned back in math 2 about how special right triangles work. And then whatever this one was R over root 2 times, R over 2 times root 3. And that was part of the special right triangles. And what that leads us to know then is that if this is the unit circle, then this coordinate right here, remember this one was 1, 0, then that means that this one right here is root 3 over 2, 1/2. And you could remember that the sine of pi over 6, remember the sine is always the y value and the cosine is the x value. So the cosine of pi over 6 is root 3 over 2 and the sine of pi over 6 is 1/2. In the same way, the sine of pi over 3 would be this divided by this, which makes this particular story 1/2 root 3 over 2. Remember, the cosine of pi over 3 was 1/2, and the sine of pi over 3 is root 3 over 2. Here's 0, 1, of course, and then, of course, the 45, 45, 90 is a nice one, because whatever this one is, this guy is R times root 2 over 2, and this one is the same. So this gives us the coordinate root 2 over 2, root 2 over 2. Now, not that all values in polar have to be based on these special angles, but it is convenient to go about it from that way, at least when we're first getting started. So now all of these things that we have right here are actually representations of coordinates in polar. And you kind of have to know that it's in polar, because you could actually go to the right 8, go to the left 8, excuse me, and go down 5 pi over 6. This could actually be just a weird point in rectangular, but it says find the rectangular for the following polar. So I'm telling you they're polar. So notice that this value right here is an R and this one is a theta. So there's a couple of ways that you could do that. One of those ways would be to draw the triangle. This says turn to the angle 5 pi over 3, which would be down here with a reference of pi over 3. This tells you that this angle, this radius is 16. That's what it says. Now remember, 5 pi over 3 would be this angle right here. It missed 6 pi over 3 by 1. Now this is this following idea. And so because of the fact of what it is, that makes this number 8, and this one 8 roots of 3, just going back to special right triangles. Now, I probably didn't draw that well. This angle is actually a little bit larger than that. So I can see that it went to the right 8, and it went down 8 roots of 3, which tells me that I need to make sure this number right here is a negative. So I could call this 8, negative 8 roots of 3. Now, that's one way to do it. Now, some people don't like to draw pictures. They'd rather use equations. So in the previous video, I told you that x was always r cosine theta. So this x value would be the radius 16 times the cosine of 5 pi over 3. And the cosine of 5 pi over 3 is exactly 1/2 because we know that the cosine of any kind of pi over 3 is a half. And I know that it's positive because, hey, we always know that anything in the fourth quadrant has a positive cosine and a negative sine. So we got 8 just like what we had right here. And y is our sine theta. So 8 sine 5 pi over 3, or if you wanted to call it negative pi over 3, you could do that as well. And the sine of any kind of pi over 3 is root 3 over 2, but it's negative because it's in the bottom quadrant. And so I think I just messed that up. There we go. That was not supposed to be 8. That was supposed to be 16. So that's supposed to be 16. And so we ended up with negative 8 roots of 3, which is exactly the same value that we got right there. In a similar fashion, for this one, if we said x is r cosine theta, so x would be r cosine theta. Now we have to stop and think a little bit. Negative 5 pi over 6 would rotate down almost 6 pi over 6. So it's in this quadrant. So I should know that based on what I'm telling you, this value right here should be negative. And I know that the cosine of any kind of pi over 6 is root 3 over 2. So a double negative makes a positive 4 roots of 3. Y is r sine theta, so here's my r sine theta. As previously indicated, it's in the third quadrant. Negative 5 pi over 6 is down here. So the sine of negative 5 pi over 6 would be negative 1/2, and I got the number 4. Now that may seem a little bit strange, but there's a reason for this. This particular problem told me to rotate negative 5 pi over 6, which should be down here, but it's got a negative radius, which we learned in the last video would tell me to go backwards somewhere up here, which is actually in the first quadrant. So it does make sense that that is, in fact, in the first quadrant, leading to both the x and y value being positive. So here's my rectangular coordinate representation of this polar value. Now, same idea here. We could do it one of two ways. We could either use a triangle, we could use purely equations. I personally am kind of a fan of using triangles. So 3 pi over 4 out 20. We should know that in these special right triangles like this one in the 45, 45, 90 case, you cut it in half and then tack on a root 2. And then you stop and think, hey, does anybody need to be negative? I know up is positive, down is negative. I don't have that. Right is positive, but left is negative. So it looks to me like this would be to the left 10 roots of 2 and up 10 roots of 2. And one of my favorite things is when someone hands me something with a pi over 2. And remember, pi over 2 is the fantastic thing because pi over 2 puts us right on one of the axes. Pi's and pi over 2's are great. So this is telling me to rotate backwards 1, 2, 3, 4, 5 pi over 2 and go out exactly 12 units along that, which is super easy because it says, hey, don't move left or right. Just go down 12 and we're done. There's nothing more to be done with that. Now, what I didn't have pre-written on this was what would happen if you didn't. So let's just try something. Let's try 2 comma 7. Now notice 2 comma 7 is not a special right triangle story. It just says go over 2 and go up 7. So what I would do is by the Pythagorean theorem, 2 squared is 4. 7 squared is 49. That would be the square of the radius. So it looks to me like 53. So the radius is root 53. And then I'm just going to ask my calculator, hey, calculator, what is the tangent inverse of 7 over 2? I'm going to make sure my calculator is in radian mode. And I'm just going to ask it, what is the inverse tangent of 7 over 2? And I got 1.292 radians. And there's nothing that I can do to do anything better than that. I just have to go ahead and pop that sucker in and see what it says. Now, what we could also do then, let's see, I kind of botched this up a little bit. I wish I hadn't made this so tight. Let's imagine that we went ahead and made the value over here at, well, let's just go with this one. How about -2 comma 7? So we already know that that's going to be root 53 from the previous example. But here's where we get ourselves into a bit of a pickle. Because according to what we just did, over 2 up 7, this is 1.292 radians. This is pi radians, which would mean the actual angle to rotate would be pi take away 1.292 radians. Well, that's a little bit strange, but let's see. That's pi take away 1.292 radians, which is 1.850. So sometimes when you want to represent it in those ways, you have to do a little bit of work. Now, coming down here, we're going to go the other direction. Let's take some rectangular coordinates and see if we could come up with some polar ones. So this particular problem says, let's go to the left 8 and up 8. Well, you can tell I was rigging this problem to be particularly kind. I made it a nice isosceles triangle, making this radius 8 roots of 2. And this has a reference of pi over 4. So what we're going to do is we're going to call this angle 3 pi over 4. But you'll notice that there's more than one way to do that. So we could have, now I'm disregarding these directions here for a second, but imagine what I did instead is what if I rotated all the way down to the bottom quadrant, down here. 7 pi over 4 would be down here. I could go backwards 8 roots of 2 to get that. Now that's not the right answer for this question right here because it says, give me some angle between 0 and 2 pi, which I did, but it says make sure that your radius is going forward. So this would not work for those directions, but this would be a valid point, generally speaking. Now this one over here, I also said, let's go ahead and do something simple. I went to the left 8 roots of 3, I went up 8, which gives me a nice little radius of 16. This is clearly a special right triangle where the opposite over the hypotenuse is, see, the sine of theta would be 8 over 16, which is a half. And hey, we know when the sine is a half, we know that the sine is a half at some kind of a pi over 6, but I can't just say pi over 6. I have to represent that from over here. So that would be the angle 5 pi over 6. Again, we're not supposed to do that according to this, but I kind of wanted to diverge just a little bit and say that there's a few other ways that I could do that. I could also go out 16 by rotating backwards 6, 7 pi over 6. Now, with that in mind, I'm going to go ahead and cancel these out because I kind of wanted to do something just a little bit different. Let's imagine, just like before, we wanted to do something where we were going to go ahead and go from, well, I guess I already did that, so never mind. I am going to go back to this problem. So I had 4 roots of 3, comma, -4. And so that's going to go to the right 4 roots of 3. It's going to go down 4, which of course is going to give me a radius of 8 because I'm referring back to one of these nice little special right triangles right here. And so if I'm looking at those special right triangles, again, I see that the sine is a half, so my radius is 8. It's got a reference angle of pi over 6 because the sine is a half. So I could either say, let's go down pi over 6, or we could say, let's rotate forward 11 pi over 6. But in this particular case, none of these things quite fit the directions. It says, hey, give me an angle between 0 and 2 pi. Well, that's great. But it says, I want to go backwards. So I've got one more thing that I could do, which would be to rotate forward to the angle 5 pi over 6, which would put me in the second quadrant, and go backwards 8 units. That's crazy. Well, I actually already found something over here. This one says, let's see if we can get there by not only moving backwards, but rotating backwards. So if I want to move backwards, I'd have to move backwards all the way to here. And again, with references that are in pi over 6, that would be 7 pi over 6, and move backwards 8. So if I rotated back 7 pi over 6, and then I whoosh, went the other direction, I would be at -8. And that kind of helps you do that. Now, the last points were just to kind of keep things going a little bit further. I tried to make this one fairly nice. In rectangular, -15, 0 is just moving to the left 15 units. But of course, that value right there could be considered at pi, 2 pi, or 3 pi. So going this direction could be the angle pi. It could also be the direction 3 pi. This tells me to pick some value between 2 and 4 pi, meaning let's not just rotate one circle, let's rotate into the second circle. So it's exactly 15 units away at the angle 3 pi. Or if you wanted to, you could say, hey, let's just rotate 2 pi, which would be over here, but go backwards 15. Or we could say rotate 4 pi, which is all the way around the circle again, and go backwards 15. And this last question is just a repeat of the others. So hopefully you can kind of see how this goes. So -12 is down here. This is 12 roots of 2. Again, I showed you in the previous video how you could take a normal coordinate and do that. But in this particular case, I'm just going to show you this one. So I've got a valid answer, but let's look up here. This says, uh-oh, I want to go backwards and I want a negative radius. So, I mean, if I went backwards 3 pi over 4, unfortunately, I'm going forward 12 roots of 2. So that's still not quite the right answer. So I've got to do one more thing. I'm going to go backwards 7 pi over 4, which is facing 100% the wrong direction, but that's okay. I'm just going to tell my person that's looking for the treasure to go backwards, and they will land in that particular quadrant. So interesting how this works out, but that's how you can play around with changing coordinates from one system to the other, plot coordinates. At this point in time, you should be able to go to the worksheet that I gave you, and you should be able to do all of the problems that are there and investigate, as well as being able to look at the Desmos activity and Desmos classroom that I'm assigning for you to do, and play around and become more and more comfortable with polar and rectangular and how they play together. All right, I hope you have a fantastic day. Please be in touch. Bye.